I want to videotape this not only for you guys that are here, but also there's a couple that are missing. The multiple choice. I'm going to say, I think I saw Brendan was the first one to finish in what, like 6 minutes?
No, I stumbled.
Oh, you were, oh, okay. So 5 minutes.
Yeah.
Now, here's, okay. Now here's the problem. With the multiple choice, you're allowed or you're allocated 1.5 minutes per question. And the bad news is when we do the multiple choice, I think sometimes we just read it and we go with our gut. But what I want to show you today is actually the answers, but also how to read the question, dissect it, because again, 1.5 minutes really is a lot of time. We only have 60 multiple choice questions on the AP exam, and being able to dissect the question, slowing yourself down, not trying to just get it over with, is going to really be helpful. So like looking at the first question, number one, and again, this is thermodynamics. And what we're shooting for is a 75%. We want to get at least 3 out of the 4 questions correct. All right, so when looking at this question here, number 1, it says for the reaction of ethylene represented above, and you've got your balanced equation given, it says that the delta H for this reaction, now listen, shh, don't talk guys, for this reaction is 1323 kilojoules per mole. It asks, what is the value of the delta H if the combustion produced liquid water rather than vaporous water? Now, and here are your options. And some of you are like, oh, well, since it's a negative 44, I'm just going to subtract that, or even double the subtraction on that. But don't forget that delta H is products minus reactants. Is that on your equation sheet? Yes, it is on your equation sheet. That's one new nice thing or nice feature about multiple choice this year. You get to use your equation sheet. So it might be that you need to stop, take a peek at your equation sheet, as well as slow down and read the question. So knowing that it's products minus reactants, and we have a negative value, then what that means is that we're going to actually add a negative 44 times 2 to the total heat that we had earlier. So the correct answer for that is D.
Ha, stupid.
And again, and Avery's not here, and that's one of the things that she and I constantly have a conversation about is it's limiting the dumb mistakes. In other words, we all know it's products minus reactants. However, it's been 3 or 4 or 5 weeks since we've worked with something like this. We have to refresh our memory. We have to go back. We have to look at things just to bring those memories back.
Hey, Craig.
Yeah.
What's the thing where you don't double it?
Bond energy.
Okay.
And that is not on the equation sheet.
Okay.
Yeah. So bond energy, and again, bond energy is different in terms of solving for it, in that you actually have to draw the Lewis structures and then find out how many bonds we actually have, and then that information for the bond energy is given to you, then you have to do the calculation. But it's, in that regard, it's reactants minus products. But this one, it's products minus reactants. Number 2, honestly, nobody should have missed this. You should, on the diagram, draw where the catalyst is actually affecting the rate of the reaction energy. So by drawing that little lowering the hump, then we can look at, after we've drawn on the diagram, okay, the catalyst was added. So a catalyst, again, does 2 things. Speeds up the rate of a reaction. We don't care about the speed in this one, but more importantly, it lowers the energy needed for the reactants to form the products, or more importantly, the activated complex. And what is this right here called? Actually, number 2. What would you call that type of energy? What is number 2? Look at your sheet. Look at your sheet. In other words, if you were asked to identify that, and I think you will be later on.
It's in this actual thing.
No, delta H is reactants minus products. So here's your reactants and products. So 3 actually is your delta H. But 2 is the activation energy. All right, so it's the amount of energy, I'm sorry, in the reverse direction, that'd be the activation energy, but for 1, that'd be activation energy in the forward direction. So if we were doing a reverse reaction, that'd be the activation energy in the reverse direction, activation energy in the forward direction. Okay.
So what do you call 2 then in the forward direction?
2 would be the activation energy in the reverse direction. So in other words, we start with this and we go that way. kind of like in an equilibrium type situation. Okay. Anybody miss that one? All right. Number 3, and again, it's about reducing the mistakes. All right, number 3, for which of the following processes would delta S have a negative value? What does delta S represent again?
Entropy.
Yeah, entropy. So it deals with not necessarily entropy, because that's what your equation sheet says. It deals with order, chaos, disorder. Actually, we want to focus on the disorder and the chaos. So if it becomes more ordered, that's a bad thing. We don't want to be more organized. The universe doesn't want to be more organized. It wants you to get more disordered. So you look at the number of particles, and don't focus on just the gases. If all the states are the same, actually, if you have the same number of particles on both sides of the arrow, then you go to the states. But if you have different numbers of particles, you don't need to go to the states. So in reaction 1, we go from 2 to 7. That's an increase in the disorder because we're getting more random particles formed. In reaction 2, we go from 3 to 1. That's a more ordered situation. In reaction 3, we go from 2 to 1. So the correct answer should have been D. Okay.
Greg, can we look at the states up first? Like,
I would not look at the states first. That is the fallback when you have the same numbers on both sides.
So could it sometimes not be the right answer?
What do you mean?
The states.
You go from like 2 solids to 1 liquid or 1 gas?
If you went from 2 solids to 1 liquid, is that what you're saying?
Yeah.
That's actually an increase in order because you went from 2 to 1. So the number of particles is the first thing you look at. If the numbers are the same, then you go to the state. Does that make sense? Now again, we're not looking at an equilibrium expression where you say, oh, well, the gas is the only one that shows up here. Okay, so don't confuse equilibrium expressions and delta S. Those are 2 different critters.
So could you have 1 liquid or 2 solid?
Yeah, but it's not likely.
Okay.
Yeah, unless the temperature's dropping. And I mean, anything could happen, but yeah. All right, number 4. Okay. You have your reaction, and it says the reaction indicated above is thermodynamically favorable. So what does that mean? That is something that I would write down. If you see thermodynamically favorable, the first thing I would write here, and I didn't do it, not positive, negative, okay? I would look at this question and go, thermodynamically favorable, that means we have a negative delta G. So that helps in answering this, and that you can cancel that off. You can cancel that one off. Then it says, but becomes unfavorable. In other words, then delta G goes to a positive sign when the temperature is increased or at higher temperatures. So again, if delta G is negative and it's favorable at low temperatures, think about delta S and delta H as being negatives as well. So again, that occurs at low temperatures. When will we have delta H negative and these are both positive? At high temperatures. Okay. At high temperatures. So know those 4 scenarios. So looking at that. Okay. At higher temperatures. When delta G is negative and delta H is positive and get rid of the plus. And delta S is positive. That only occurs at high temperatures because the reason why, if we look at our equation, delta H minus T delta S, if we have this as being positive, which we want, and this is positive, if T goes higher, what happens to the back end of this equation? Gets more negative. So for the situation where we have a negative delta G and it is spontaneous at high temperatures, is because that's our scenario.
Why is D wrong?
D, delta G and delta S are negative, which is true, but delta H is positive, so we don't have a...
Right, but it's possible for it still to be thermodynamically favorable and then become...
Under this set of conditions. What you're saying is every single time. Or I'm sorry, no. If this is positive, actually, it's never going to be. Delta G would never be negative under those conditions. Yeah, sorry.
Why not C?
Why not C? Let me erase it.
Yeah.
So delta G and delta H are negative, but delta S is positive. That would be under every scenario. So, okay, so here's the question that's asked. Why is C not the answer? Because it says that it's favorable at low temperatures, but when the temperature gets higher, then it becomes unfavorable. So as soon as that temperature gets high enough under this set of conditions, then this back end of the equation becomes positive. Okay. So, and again, hang on, guys. Shh. So what we have to look at is what the question's giving us, not when it's delta G is negative every time. Okay, that's the question. Okay. So again, RTF. It's good to know when it is spontaneous at every temperature, but this question didn't ask that. All right.
Mr. Craig, it's RTFQ.
Thank you. All right, number 5. It says a student observes that an open container of water left overnight. What's the matter?
He goes, yes. He hasn't got one right yet, and he goes, yes.
Because you were so fast. You didn't have a chance to read them. All right, number 5, it says a student observes that an open container of water left overnight in a laboratory experienced a good deal of evaporation. In other words, if I leave a container filled with water overnight, is a lot of it going to evaporate? Overnight? No. Over months? Yes. But overnight, that must mean that either the room was warm, maybe it was on a hot plate that hadn't been turned off. So either all the water evaporated, but a good deal of it evaporated. So in that case, that means that the delta H, that water is absorbing that energy. So that's why delta H is positive. Delta S is positive, which means that it's becoming a gas, more disordered. So in other words, it's going from a liquid to a gas. So that's why A is the best choice. B is saying that it's getting more organized. In this case, it would be absorbing energy and turning into a solid. That's what B is saying. And then we know that C and D can't be right because it's not losing energy. If it loses energy, then it turns into a solid or moves toward the solid state. What's the matter? Okay. All right. Number 6. And hopefully you're making notes along. These are study guides for you to use. Number 6, it says, which of the following thermodynamic quantities best describes the combustion of liquid pentane? Do we care about liquid pentane? No, it's just pentane. So, but the combustion of that, and it forms carbon dioxide and water. So we know that all combustion reactions are exothermic. It's going to lose energy. So right off the bat, you can get rid of A and B. Okay, they're not absorbing energy, they're losing energy. That's why we use it as a heat source. And then we have to look at the other scenario. After we balance the equation, is it becoming more ordered or more disordered? So it goes from 9 particles on the left side to 11. So it's increasing in disorder. Okay. Now, I will say that looking at that and analyzing all of that, a minute and a half is a long time. Try to hold your breath for a minute and a half. Not right now, but that is a long amount of time. And some of you are like, it's got to be quick.
Would you actually write out the whole balanced equation on that?
You would want to if it's asking about delta S, because this doesn't give us any information about it. Yeah, liquid could lean that way, but if we had, say, an 11 and a 9 here, then my answer would be B as in boy.
Even with the liquid?
Even if it's a liquid, because again, when you're looking at delta S, guys, hang on. Shh. So even though it's a liquid, you look at the total number of particles. So that's the first thing you look at, and then you go to the state. If it's just saying goes from methane, 1 of those to 2 of those, then it's a no-brainer. Okay, that definitely is a positive, delta S. All right, number 7. Which of the following best describes the energy required in the transition? So right in there. So free energy, that's determining whether a reaction will take place or will not take place. So that's plus or minus. The ionization energy. What is ionization energy?
The energy it takes to
Remove electron.
Gain electron.
So remove an electron, very good. And who does it favor? Is it low on the metal side or is it low on the non-metal side?
On the metals.
Metal side. Metals want to give it away, so they have low ionization energies where metals have higher. Why is that?
Because they want to get a full electron.
Coulombic attractions, very good. Zeph.
Zeph.
Okay, we'll talk about those later on. Kinetic energy, that was just something they threw in there. That's just the energy of motion. And then activation energy is your best answer.
I got that one right, Mr. Craig.
Good job. All right, number 8.
Good job, Sam.
Gosh damn.
Compared to the value of delta H for solid water, the value for delta H for liquid water has... Now again, what does delta H with the little f on there mean? It's the heat of formation. So it doesn't matter if it's a solid, liquid, or gas. The heat of formation for water is still water. It's the same value. However, if we're going, and I put on here, the heat of formation for water is negative, and it won't change. It doesn't matter if it's a liquid, a solid, or a gas. However, the absolute value, and again, that's not something that we really talked about, but it's dealing with how much energy is it giving off. In other words, from the natural state that water goes from. Is it more giving off more as a solid? And it is. And then it's last for the gas because water wants to be more of a liquid / gas.
Mr. Craig,
Yeah.
I said that it takes more energy to create a solid than liquid. Is that right?
It takes more or you lose more?
Oh yeah, you lose more.
You lose more.
Create a solid than liquid.
Correct.
Why is it the absolute value?
Absolute value is not a term that we use at all, I'll be honest with you. But it's dealing with how far away from the heat of formation. And where does heat of formation, at what temperature are we talking about for heat of formation of something? Room temperature, right? So, in other words, to go from a solid, it doesn't take very much. To go from a liquid, it takes, actually, yeah, going from a liquid to a gas. Yeah, the solid loses the most, where the gas actually gains. Okay, so there's a difference on that. All right, number 9. How are we doing on time? Good. Which gives the thermodynamic parameters for the phase change in a system that begins as an open container of liquid water placed in a constant temperature environment of 230. Now, did any of you recognize or even blink at the 230?
No.
Nope.
Yeah. 230 is extremely cold.
I was thinking Celsius, that was really hot.
Yeah.
That's freezing, isn't it?
Oh, it's well below freezing. Freezing for water is 273 Kelvin. So this is almost 40 degrees cooler. So if I take a container of water and I expose it to this temperature of 230, what's it going to do? It's going to freeze. Is it going to gain or lose energy? It's going to lose the energy. Is it going to be spontaneous? Is it going to freeze if I just put it in that 230 environment? Oh yeah, so delta G should be negative. And delta H is negative because it loses energy. And delta S is also negative because
Becoming a solid.
becoming a solid. Okay.
So it's becoming more ordered.
It's becoming more ordered.
Wait, which is the one? I thought there was one I was doing, and it was like they can't be the same sign. Like, is that
The scenario where it'll never be a negative delta G is where you have a positive delta H and a negative delta S. That's where it'll never be spontaneous. So in this case, we are losing energy and it's getting more ordered. Yeah.
I've got
Okay?
3 right.
And the last one. What's the matter?
We got you right.
8?
Yeah.
Oh, nice. All right, which describes the direction of change in enthalpy and entropy for an endothermic dissolving process. Did everybody see that? It's endothermic, so delta H is positive. Dissolving, so therefore the entropy is positive as well. Okay? So in other words, what's happening is it's absorbing energy, endothermic, and it's also going from a solid to ions. So it's getting more chaotic.
Mr. Craig's enthalpy delta H?
enthalpy is delta H, and it's on your equation sheet as well.
Oh.
If you look on the right-hand side, on the thermo side, it'll tell you that. Okay? So again, this is really one of the first times that we've formally gone over multiple choice questions. We're going to do it a couple more times. I think the next quiz, the next A-Day, might be a multiple choice question. Now hang on. Now listen. Shh. Now listen. It won't be over thermodynamics, I promise you that. However, take your time. And I noticed that a lot of you finished very quickly. Start to look at the question and dissect it. Read it at least 2 times. Trust me, you're not pressed for that much time.
Right.